In Rett, the brain is smaller than normal, and the neurons are smaller and closer together with reduced connections, especially in the frontal and inferior temporal areas concerned with thinking, movement, fine hand skills, and speech. Donna Armstrong is a neuropathologist who has carried out much of the research into the structure of the brain in Rett disorder. Here she explains what is seen in the brain.
So Donna, what do you consider the most significant distinctive changes in the brain in Rett?
Well, from the gross appearance of the brain, the small size, from microscopy, by regular studies you may suspect that the neurons are small, that they may be more closely packed with each other, but you really need special studies to show alterations in the dendrites. Well, the changes in individual neurons with less branching of the dendrites and less points for synaptic contact.
Have you found any evidence of degeneration in the brain in Rett at any age?
No, there's nothing consistent that I would say is related to the degenerative processes.
MECP2 has an important role in neurons and their synapses as they become mature. Neurotransmitters, the brain's chemical messengers, and the receptors for them, normally active at synapses, are profoundly disturbed by a lack of MECP2. Here, a part of the cortex has been stained to show the receptors for glutamate, the main excitatory neurotransmitter in the brain. On the left, we can see the density of these receptors in the healthy child at 2 years old, and below at 10 years, when there is some increase. By contrast, on the right, we can see that the child with Rett has greatly increased density of receptors for glutamate at 2 years, and they have almost disappeared by 10 years. This image shows a reduced level of serotonin transporter in the dorsal motor nucleus of the vagus nerve in the Rett brainstem, on the right, as compared to normal on the left. Serotonin transporter expression controls serotonin levels at the synapse, and since this nucleus regulates preganglionic parasympathetic outflow, modulating heart rate and gastrointestinal function, this defect might be expected to contribute to parasympathetic problems, including cardiorespiratory control and gastrointestinal function in Rett. The brainstem neurons that regulate respiratory and cardiac rhythms are probably amongst the first to be affected by lack of MECP2 even before birth. They are part of the central autonomic nervous system that organizes activities essential to normal bodily functioning without requiring thought, such as the rhythms of the heart and the lungs. The blood pressure sensors, baroreceptors, in the aorta transmit information to the nucleus solitarius and so to the nucleus ambiguus in the brainstem, which adjusts the heart rate through the vagus nerve and the sinoatrial node to keep blood pressure, pulse rate, and therefore cardiac output stable. This is the baroreflex, and its influence is a restraining, parasympathetic one, balancing the effects of the sympathetic nervous system that, unrestrained, would automatically increase heart rate and blood pressure. The sensitivity of the response of the heart rate to changes in blood pressure is called baroreflex sensitivity, and the flow of information from the brainstem to the heart through the vagus nerve is called vagal tone and can be measured. In Rett, this parasympathetic restraining influence is at a low level, similar to the newborn level, which leads to impaired control of heart rate, blood pressure, and breathing.